Hello everyone, how's everybody doing? I hope you're doing fine. Hope the virus didn't catch you. And today we have another exciting physics day. Anyways, I'm going to start, I'm going to be talking about Mr. Casimir and the expansion of the universe. We have these two notions. Hello everyone, how's everybody doing? Whoa. I had my, let me make sure I'm okay here. Anyways, we have on the one hand Mr. Casimir, who talks about compression, and then we talk about expansion of the universe. So we're going to be looking at that today. But before that, we get into that, we want to talk a little bit about this little thing that happened yesterday. Mr. Elon Musk, he sent his SpaceX to space. Here it is. And I guess it was to prove that the Earth was round to the flat earthers. Yeah, it was launched, and the idea behind this is that they want to go eventually to Mars. And I guess there's a competing group headed by Mr. Bezos, and he wants to go to the moon. One guy wants to colonize the moon, the other guy wants to colonize Mars. What do you think of that? Well, I can tell you what I think of it, and I've already said quite a bit of that in my book. We're never going to go to the stars, which is one of the people who was interviewed yesterday by the media, and he's saying the ultimate goal is to go to the stars, to expand our seed throughout, I guess, the galaxy, and that's never going to happen. At all. It has no chance whatsoever. It's surrealistic. It can never happen. It's not even within the realm of possibility. The first thing we have to figure out is why we're going to Mars. Are we going there? Here I've got a little breakdown of that. Okay, are we going to Mars, to evacuate the Earth? Are we going to evacuate 8 billion people and get the hell out of here because we can't stand this any longer? Especially we can't stand our politicians. Are we going to explore? Is this just a scientific project where we go to Mars and to even other star systems for that matter? Well, are we just going down there to explore, to see how nice everything looks? Yeah. Or are we going to colonize? Are we going to send people out there? Imagine we have to go all the way to Alpha Centauri, the nearest, it's a 3-star system. The nearest star, I guess, is Proxima Centauri, 4.3 light years away. That means traveling at the speed of light, right? 300,000 kilometers per second. We reach one way, 4.3 light years. At 4.3 years. Round trip, 9 years, rounding off, right? 9 years, round trip. Are we going to put a colony over there of humans? For what purpose? I mean, are we going to trade with these folk over there? We're going to take 9 years to take bananas over there, and they're going to take 9 years or 4 years, whatever, 5 years to bring steel or some metal that we need that they found over there in a planet near Proxima Centauri? No, obviously you got to be deluded to think that we're ever going to go to the nearest star. And so the question, why would we want to go to Mars now? Let's get a little closer. Why would we want to go to Mars? So what are we going to do in Mars? We're going to put a colony? Are we going to terraform the planet, as Mr. Carl Sagan said once? We're going to go in there and change the air. In other words, change the CO2 to O2. We have a smaller planet, as you can see. It's about half the diameter of Earth, and it doesn't have as much gravity because of that, because it doesn't have as much mass, retaining its atmosphere. So it's got a thinner atmosphere. Even if we were to make O2, it'd be thinner, because it wouldn't have the gravity to hold it down around the surface of the planet. So what are we going over there for? Are we going to go to colonize? What are we going to do? Take all the prisoners out of prison and a gunpoint, tell them to go into the spaceship and send them out? Is that what we're going to do? No, we're never going to colonize Mars. We might make a trip. We have probably the technology, or can develop the technology, given enough time to reach Mars, and maybe walk around like the rover, go around a little bit and then come back, that kind of thing. We might be able to do. Everybody's going to clap. Very expensive experiment. Again, exploration, just a little science experiment. And governments usually treat NASA as one of those, okay, a science experiment. Let's give them some money. So they give them very little money compared to the importance that they should have. You would think, when we're going to evacuate the Earth or going to colonize Mars, we might as well give them a lot of money. That's never going to happen. Congress is never going to fund trillions of dollars to go to Mars. And for what? Just to found a colony? Again, what are they going to bring back? Bananas, apples, Martian potatoes from the guy who got stuck over there? What are they going to bring back? Is it going to be cost effective to trade with the Martians, the people over there? No, it's never going to happen. This is just nonsense that people think about. By the way, I used to think about that also. I thought we were going to colonize the galaxy. Man, I got away from that idea. Anyways, I don't think this is ever going to happen, especially in light of, now we have riots in the United States, many cities. And this could be a temporary thing, but maybe it's a more permanent thing where we're going to see more and more people go out into the streets. Not because of police brutality, but for something else. And that's what happened before, and that's this coronavirus thing. Wear your mask, even if you are rioting, you better wear your mask, or they'll arrest you for wearing the mask, not for stealing or looting or whatever. So yeah, I mean, here you have this. Not the coronavirus, because I personally don't care about that coronavirus at all. I don't even think about it. I think about the economic consequences, and there are important economic consequences. And for those of you who've been following my theory, for the last 20 years, I've said that we're the last humans on Earth because the global economy is going to disintegrate completely. And what I mean by that is trade will be no more. A lot of people have problems with that. They say, what do you mean trade will be no more? They're so used to trading. We're so used to doing some of these things that everyday things that we trade, and we think it's normal. No, it's not normal. For most of human existence, if our species, let's say, lived 200,000 years, a very small percentage of that, maybe 4,000, 5,000, 7,000 years, I would think, last 7,000 years, that's the only time we did trade. For most of human history, all we did was hunter-gathering. We were just another animal in Eden. That's it. And so, no, trade did not exist and will not exist in an asphalt jungle. The only thing of importance is food. You don't trade food for food. But, the Disneyland economists never learned that. They think they can go in there and exchange their car, which has value, as they call it, value. That's their key word. It has value. And they're going to trade value for value. And they're going to trade their car for, I don't know, a bag of potatoes. No way. The guy with the potatoes will win. For sure. Anyways, here we have Mr. Trump, and he's quite angry with all of what's going on, and he should be. He should be upset. It upset a lot of his plans, I guess. And on the other side, you have this fellow and Xi Jinping, and he's laughing at Trump. He said, look at all the problems Trump is having, with the corona and with the riots and so on. Well, my take on this is that Comrade Xi should not be laughing too much. And again, I said it 20 years ago, and I'll say it one more time, and here it is. The day that the U.S. economy collapses, it'll be the end of the world. There will be no Chinese empire or Russian empire. The last empire on earth will be the United States. And when the United States collapses, that's it. All the countries are hanging on to the United States. And until you understand that from a macroeconomic point of view, you have not understood anything about economics. Okay? Every country in the world depends on the United States. That's the center of the empire, Washington, D.C. And when, not if, but when the United States government finally disintegrates, in other words, when money will be no more, at that point, all the countries are in trouble. Every human on earth is in trouble. That's my take. Take it or leave it. Okay, but that's essentially what I'm proposing. Anyways, let's get to a couple of the questions that people raised. Here's the fan mail. Here's one fellow, and getting more into the subject of today, he says the mediator of gravity is intangible. Therefore, it is irrational by analysis of the definition of the words used to describe it to use the language of tangible things to describe it. Gravity does not inherently require a mediator. Whoa! The phenomenon is an inherent characteristic of the objects. Well, until someone can explain gravity, that's just a statement with no teeth in it behind it. But let me show you what the problem is with that. Here you have the astronaut. He's being carried down to Earth by angels. Is that what he proposes gravity is? Some kind of spirit or angel? I mean, we have to explain this. We have to explain why the ball falls to Earth. Is it taken down by an angel? Or a spirit? Here's the ball falling by gravity, right? Is it pushed down by an angel or, I don't know, attracted by some rubber band or something? You got to explain that phenomenon to say that it's just a property of the ball. Well, what do you mean by that? What does that possibly mean? You have to explain the mechanism of why that ball falls to the ground. In other words, what causes it to fall to the ground, okay? And if you don't put, hold it, I got the wrong one. If you don't put a physical object in contact with the ball, then all you're doing is just verbiage. I mean, here I have a little ball. Okay, here's my other hand. Here's this hand. I let go of the ball, right, and it falls to my hand. By the way, no strings attached. Okay, and here, let me do it again. Okay, I let go of the ball, and there it falls. Okay, falls on the floor, okay, or on my hand, right? Here it is. Okay, so if I let go of the ball, it always falls to my hand. You can do the experiment in your house if you believe in experiments. The question is there something here in between the ball and my hand? Or is there something pushing on the ball? I mean, I didn't push it with my hand, and I don't feel anything pushing on my hand. I'm holding my hand up here and let go of the ball, and the ball just falls. So the question is, either something is pushing on the ball or something is pulling on the ball. There can be no third possibility. And so you have to identify whatever comes in contact with the skin of the ball. That's the trick. And that thing had better be invisible and intangible. Why? Because a thing is not that which you can see or touch. A thing is what? That which has shape. Okay, and so that's where we have to start. If a thing has to have shape, that's it. If that's the only property, that universal property of all objects, then not all objects can be seen, or not all objects can be touched. Okay, so touching, I can't touch that gravity that was in there between my two hands that somehow compelled the ball to fall downwards. The ball never falls. I can try it in reverse here. And I can wait all day, but that ball will not come to the other. I'll have to throw it upwards for it to come to my upper hand. So no, you got to identify the invisible entities Mother Nature uses to do gravity. That's the trick. That's the magic trick you got to figure out. And it's got to be kindergarten stuff. I'm sure, like I said in my Spanish channel, explaining how a car works has to be infinitely, to use that word, or at least 1,000 times more complicated than explaining, why a ball falls to the ground. The mechanism. It's got to be a much simpler mechanism. And all you got is push and pull. So you figure out if it's going to be push or if it's going to be pull. With particles, you can push. With a rope, you can produce the pull. It doesn't pull like an elastic or anything like that, but It's I've explained that in the past. But the point is that you can explain it with ropes. Once everything is connected, physically connected, then you can explain it. But with particles, well, good luck with that one. That's all I can tell you. Okay, another issue brought up by another follower here, a person who questions the rope model. Okay, says, look at the interconnections. Now imagine trillions upon trillions. Okay, what is he talking about? Well, he's talking about the connections. Under the rope model, okay, we have this situation, okay, where all atoms are interconnected, okay, and that differs from the quantum mechanics, which has this situation. You have all particles are individual, discrete entities. And so that's the difference. And what he's talking about is those connections on the right-hand side, which are under the rope model is the rope hypothesis, right? It says that it's a rope-like mechanism that cannot be seen, cannot be touched, it can only be imagined. And why? Because it's a physical object. And what's a physical object? That which has shape. That's the logic behind that, okay? That's the rationality behind that. Okay, so he's talking about those connections. He says, well, but if you have all these ropes crisscrossing the universe, or even here on Earth, we got gazillions of ropes. He's saying, what did he use? He said, with trillions of trillions, I think. Yeah, he said trillions upon trillions of ropes of interconnection just crisscrossing. Well, we've got a problem where, well, first let's explain our side of it. We have trillions and trillions, but we don't have infinite. See, when you look at quantum mechanics, they talk about infinite whatever, because mathematicians like to use that word infinite and infinity. Infinite numbers, infinite fields, everything is infinite, right? And so with that, they get rid of the questions from the reporters. What's infinite? We're done. It's like, don't ask any more questions. They leave it up in the air. And under the rope model, no, it's finite, okay? There's a finite number of ropes in the universe, okay, because there are a finite number of atoms in the universe. Why? Because ultimately all there is, the underlying hypothesis is this: it's a single closed loop thread. There's a single closed loop thread in all of space, and that thread twirls around, goes everywhere, constructs the atoms, the ropes, and it looks more or less like this. You have this twining of this single thread, and it turns out into all those gazillions of ropes that interconnect gazillions of atoms. Okay, that's our universe. That's the proposal. Okay, that's what you have to visualize. Okay, so the question is, how come those questions are not raised with quantum mechanics, with the particle hypothesis? I'm sure this fellow never asked that question in terms of quantum mechanics, or even in the case of relativity. I mean, when you look at the universe, right? Well, you'll find something like this. You'll find gazillions of stars and galaxies. And so to talk about, how can there possibly be trillions and trillions of galaxies? How can there be trillions and trillions of stars? Well, yeah, that's our universe. I'm sorry, And then the question comes to quantum mechanics. Here you have two atoms, and supposedly, according to especially what we're going to talk today, about, is that we have all these particles that form what they call space. Space, according to mathematical physics, is made of particles, and those are virtual particles. And so the question is, how many particles are there? I mean, are there trillions, gazillions, especially when we're creating new particles every day according to mathematical physics, particles that come in from the void, and space is expanding, and if space is expanding and space is made of particles, we should have an infinite number of particles. How come they never asked this question in terms of quantum mechanics? I mean, they ask two things about, typically, about the rope model. How is it that I can't see the rope? How come I can't touch the rope? How do these ropes manage to go across each other? Or how come they don't get tangled, all these gazillions of ropes? And how can there be so many ropes? Well, now let's ask those same questions for quantum mechanics or the particle model of mathematical physics. How can two particles, in fact more than them, because they say any number of particles can be at the same place at the same time, they superimpose. Particles in quantum mechanics can be at two places at once. How many particles are there in quantum mechanics? I mean, not in the standard model. I mean, really out there. I guess gazillions? How many atoms are there in the universe? Are there gazillions? Are there infinite number of particles? So how come they don't ask those questions in the context of quantum mechanics? Why does it occur to them to ask those questions only in the context of the rope model? And so the answer to such questions is the day that you can answer, okay, how many particles there are in the universe under the quantum mechanics, and how two particles can occupy the same space at the same time, and how can one particle be at two places at once? When you can answer that question, then you can ask that question under the rope model. How's that for a deal? Okay. You can't ask that question until you answer it first with particles, because no one asks those questions in the context of particles. How can two particles be at the same time, in the same place? How can they collide and at the same time also be at the same place at the same time? In other words, how can they merge and also collide? And how many particles are there? That's the question you got to answer. Okay. Then when you answer that question, I'll answer how many ropes there are and how trillions of ropes can be crisscrossing and be at the same or in the same vicinity or whatever. Okay. We move on to the subject of today, which is Mr. What's his name? Brian Greene. Brian Greene, good fellow. He was saying the other day that space is made out of material, out of particles, out of things. Under quantum mechanics, it's made out of particles, and under quantum mechanics and under general relativity, it's taken as this, I guess, fishnet, canvas, whatever you want to call it, some elongated thing that they call a field, okay? It's supposed to be some kind of gravitational mass field, whatever. You're supposed to think of it, visualize that any way you can, okay? And so these are the physical interpretations. Again, we're not referring to the equations because we don't care about the equations. We care about their physical interpretations. And so when these people come out there and they say, well, here they're made out of particles, over here they're made out of fields or some kind of canvas, some kind of continuous medium, right? Well, in both cases, they're talking about something physical. Okay, they're saying space is a physical entity. Under the rope model, that's easily debunked because we say that an object's that which has shape, and the only thing that quantum mechanics has to answer is what encapsulates each particle of space. We want to know what the other stuff is. In the case of space-time, same question. What encapsulates space-time? Is it the fifth dimension, which is encapsulated within the sixth, and so on down the line? I mean, at some point you have to identify the last medium that encapsulates it all, and that we under the rope model we call nothing, and that's space. Space and nothing are synonyms. Vacuum, same thing. They all mean the same thing, and that is that which has no shape. If something is that which has shape, nothing is that which has no shape. Very simple, very straightforward. Anybody can understand that. The nonsense of quantum mechanics, the nonsense of relativity, nobody can understand that. Even they admit, the mathematicians admit that they don't understand their own theories. They confess this. Okay, so what they did in mathematical physics is try to prove. They always prove things in mathematical physics. So they try to prove that space is a physical object, okay? Malleable, probably in some cases. Other people consider it something very rigid. So we have one guy, Australian guy who wrote a book saying that it's 40 to the 10 to the 40th uh, times stiffer than steel. That's what space is. That's how rigid space is. And other people say, no, it's a malleable thing. It's like an ocean that waves around so that you can send gravity waves. And so they have these discussions about whether that material space is flexible or it's rigid. So that's one of the issues that mathematicians fight about. In rational science, we dismiss that as nonsense, all of it. Space is nothing. There is nothing there. Okay? The only thing that exists are the objects, and those objects are the atoms. Atoms are interconnected by ropes, and there's a single thread that underlies all of matter and turns into atoms and then into ropes and so on down the line. Okay, but anyways, where does Mr. Brian Greene begin? Well, he begins over here in with gravity probe B, one of the proofs that space is a physical object. And he says that they ran this experiment NASA did about, 1977, thereabouts. And they showed that, essentially the Earth drags space around itself. Okay, so that's that fishnet that Earth is dragging around, that's supposedly space, or space-time, if you will. And they ran these perfectly made gyroscopes, and they were able to prove that the gyroscopes were dragged along with that dragging of space. And that's how they proved that space is a physical object that can be dragged around by the spinning of the Earth. Okay, so that's one of the proofs, right? Another proof was this Higgs. They had Peter Higgs, a British guy who received the Nobel Prize for his brilliant idea. And this guy came up and said, look, there's this ocean out there, which I guess Mr. Paul Dirac called the Dirac Sea, and people before that called the ether, and so on down the line. This is a sea of particles. And some say, well, no, it's not the same thing because these are negative particles. Okay. Particles is particles is particles, okay? Period. People are proposing that space is made out of particles, and all you got to identify what encapsulates each particle. Again, that's all they have to identify. But they came up with a Higgs field, and the Higgs field is also, I guess, part of space. I guess all these particles are fighting for space. You got the virtual particles, then you have the Higgs particles. And what are the Higgs particles? Well, these are particles that form the ocean of space, or part of it, I guess. They've never clarified that. And when any real particle, I guess you can call, like atoms and so on, and upwards, tries to pass through this so-called Higgs field, this ocean, well, some particles are affected more than others. And that's what determines their mass. And here's a little picture that Brian Greene put out, okay? Next, something like this. Let's see if I can make this a little bigger here. Okay, and more mass it has means that the more a particle interacts with the Higgs field. That's essentially it. So one goes right through the Higgs field without any problem. The other one has a lot of trouble getting through there, and that's the difference in mass according to the mathematicians. Okay, and so this is how they explain gravity, in other words, or mass. In other words, they're saying, one particle has more mass than another simply because it interacts more or less, depending on the mass, right, with the Higgs field. So that's the bright idea that they came up with. And what that means is space is not only made of virtual particles, and maybe tachyons and who knows what else, but it's also made of the Higgs particles. These particles form this ocean of particles called the Higgs field, and mass is explained in terms of a particle, or a real particle. I hate to say this, but I have to talk in those terms. A real particle trying to get through this ocean of particles called the Higgs. And he got a Nobel Prize for this. Yeah, you'd be surprised, but this is what they give Nobel Prizes out for. Can that explain why the ball fell? Here's my little ball. Can that explain why? Is this going through the Higgs field? Is it being pushed by the Higgs? I don't know. Right now it's resistance to the ball. And again, all these theories come from their mathematical gibberish, which has nothing to do with physics. And they reach these conclusions. They draw these conclusions from the equations. They say, well, this equation suggests, that the physical interpretation is that there is an ocean there, and mass amounts to resistance going through that ocean. This or you can call it molasses. So one particle is not affected by the molasses, goes right through, and like say a lead ball might fall faster through the molasses than this little rubber ball that might float in the molasses. And that's the idea. They get all this nonsense again from equations. They give Nobel Prizes to each other for these things, and we still don't know how gravity works. Here we are. We're still trying to figure out simple things. Okay, the other experiment where they proved that space is a physical object comes from a fellow from Holland. His name was Casimir, Hendrik Casimir. And Mr. Casimir, he proposed that space has the power, has the muscle to push two plates together, two metal plates together. So if you put these plates in a total vacuum, let's say 100% vacuum, let's say assume you could achieve perfect vacuum, nothing in there at all, right? Whatever vacuum is, nothing, but the empty space of mathematical physics is always full of something, but we're talking about a total nothing. There's nothing there, no matter whatsoever. And if you put two plates there, they'll come together. If you put them very close to each other, okay, there's got to be, the distance is important. It's got to be a very, very tiny distance between those two plates, okay? And what happens when you put the plates in there very close together, for some reason, they come together. And so this fellow Casimir, he wrote a paper in which he showed that that's what would happen. And until the end of the century almost, they weren't able to so-called prove it. They finally ran an experiment, they measured, and they said, we've proven Hendrik's prediction, okay? And here it is. What's his name? Brian Greene. He says there's more frenetic activity of particles on the outside than on the inside, and what happens is the two plates come together. They should have squashed them there, but he got out on time. Anyways, he said that empty space, the plates were pushed together. And that means that Casimir predicted that if you take two ordinary metal plates and place them extremely close together, then particles with certain energies would be excluded because they wouldn't fit between the plates. Okay? And with more of these frenetic activity outside the plates than inside, the plates, I guess, would come together. Okay? And so there's no such thing in mathematical physics as empty space. All you have is particles, okay? And what Brian Greene was saying essentially is there's fewer particles on the inside pushing the plates apart than on the outside pushing the plates in. And because of that, the tug of war is won by the particles on the outside, which manage to squish the particles out of existence or whatever in between. And again, they're talking about virtual particles because they're talking about empty space, and they're saying, well, there's activity over there. And what we think of as empty space is not really empty. It's full of stuff, and they call them virtual particles. Particles that pop in to existence at the whim of the mathematician, right? And they produce these effects because they can't explain them otherwise. And they say, well, the only way we can explain it is if we invent particles and put them here and there wherever we need them. And you say, well, where'd you get the particle? Well, we got it from space, see, because space is full of seizing energy. Energy is mass in a different format, and these energy particles, I guess, turn into mass particles. They come into existence, or charged particles. They come into existence momentarily just to fool the mathematician and then go back into nothingness. So we have these particles that go back and forth, and you would think that a particle is a particle is a particle, but no, they have real particles and virtual particles. Virtual particles is a magic particles, one that comes out of the wand of the mathematician. That's what it is. And here you have another version which I created for the Casimir effect so that you can see a little better maybe what they're talking about. Okay, You have two plates. Vacuum is made of virtual particles, remember. You have virtual particles between the plate, those yellowish kind of particles, but you have more on the outside, obviously, and so they push them together. That's the Casimir effect. Okay, but keep in mind that this is one version of the Casimir effect. Um, there's another version based on waves. Okay, that they say you have the length of a wave, and if you don't have the full wave, or you have half a wave, or you have only 1.5 waves in there, okay, more than that can't fit between that distance between the plates, and so you don't have enough wave pressure to keep the two plates apart. And so, if you had a longer wave, maybe it could withstand the plate from coming together. But if you put the plates very close together, you're kind of squishing the wave in there, okay? Because particles are waves are particles, right? So you have this half wave, or you have a one wave or a 1.5 wave, and that's not enough to keep the plates apart. And the waves on the outside squash them together. So they have two versions. One is the particle version, the other one is the wave version. Quantum mechanics likes the particle version. That's the one Brian Greene favors there. And he just says, there are more particles on the outside than on the inside, and that's what squashes, the plates together. What is the rope model? Okay, well, here we have a rope version. Okay, between the plates you have ropes. Okay, you have every atom from one plate connected to every atom in another plate. Okay. And again, I didn't draw the gazillions of ropes or atoms as this other fella would want. Yeah, I didn't draw them all. So all we know is that under the rope model, all atoms are interconnected from one plate to another. Okay, and what happens on the outside of this? Okay, see if I can put it up here. We have also, atoms in the air or in the vacuum, because we never have total vacuum inside a chamber. And there could be more pressure on the outside than on the inside. Yeah, no problem there. But again, the plates could be drawn together also by gravity. Again, they don't consider gravity because they don't have gravity for quantum mechanics. They have no explanation for gravity. But under the rope model, if you have two objects very, very close together, yeah, you have the standard explanation that I give for gravity, which is as two objects approach one another, right? What happens is the ropes fan out. And as the ropes fan out, the more they fan out, the faster they are drawn together. In other words, the faster the acceleration of one object with respect to the other. So no problem with the rope model. It could be explained with gravity. One of the reasons they do not like to include gravity there is they say gravity is very weak force in comparison to electromagnetism. Well, that's just nonsense. That's measurement that they do without understanding what they're measuring. Okay, they're measuring angels. They don't even know, they have no idea what they're measuring. And the issue here is that, yeah, any two objects, we know this from running the, the Cavendish experiment. You have two lead balls, and they're strung on a wire that can turn, okay? And you put two heavy objects next to them, and that torsion balance, as it's called, will twirl until one object strikes the big weight that you put there, and the other one strikes the other one. So it'll twist the thread, and the twisting, they can tell that's how they determine the gravitational constant G. Okay, so we know that at close distances, gravity acts very well. And so to say that there's no gravity involved in two metal plates, very close to each other, that there's no gravity acting there, well, that's an issue of faith. That's what it comes down to. Okay, but they also proved it on a large scale that space is a physical object, and one of the key issues there is this Big Bang theory, and that's been around since the 1920s at least. Okay, and it looks more or less like this. Okay, says that we had this Big Bang explosion. What is it, 14 billion years ago? And here, let us start. Okay. And according to them, 14 billion years ago, we had this great explosion known as the Big Bang. We don't know where it came from. In a fraction of a second, the universe underwent a violent expansion. Okay. So we had all this stuff hurtling outwards, really space. They say space is hurtling outwards, and space has been expanding ever since. And all I see is the explosion of matter, but they say it's space that is expanding, pushing the matter outward. So you have to understand exactly what mathematical physics says. First of all, we have no idea where this Big Bang thingy came from. In other words, according to Stephen Hawking, there was energy to begin with. We don't know how it got there. Maybe God made it. I don't know. But there was this energy, this concept called energy. And this concept, exploded. Somehow separated from positive from negative energy, and it exploded. And it's this which creates the universe. That's their explanation for the origin of our universe. The point is that from this Big Bang singularity, right, point, in where? I don't know where, because there was no where. Space did not exist. And so I don't know what existed if there was no space. Not even God could exist without space, It's so the issue is they have this point and it explodes, okay? It explodes, creates all the matter that we have today. Okay, it's been expanding ever since. But the key issue is that space is a physical object, okay? And you have to think of it as expanding and pushing galaxies and stars and matter apart, okay? And so that's the idea that they want to convey to you, okay? And that's one of the reasons they have to take space as a physical object. They cannot allow space not to be a physical object, because all of mathematical physics would collapse in a picosecond, okay? Okay, and so one of the issues that came up is whether the space will expand forever, because if space is expanding, you would think that at some point maybe it turns the corner and starts coming back into what they call the big crunch. So we have this oscillating universe theory where you start with a big bang and with a big crunch, it expands and comes back and ends with a big crunch. And then you start all over again. Big bang expands until a certain point and then comes back and ends up in the big crunch. And they illustrated that as well. And here it is. You have the Big Bang here coming up. Okay, it's ultimate fate of the cosmos. What is it? And would space go on expanding forever, Greene says, or asks? Or would gravity eventually stop space from expanding? And then it all comes all the way back, causing it to collapse back on itself in a big crunch. Blip. There it goes. We start all over. Is that what we have? We have an oscillating universe. Well, they concluded that no, they proved, they always prove. They proved that that's not the case. Okay? They proved that's not the case. So what is the case? Well, they had to show that if, because the idea came from this notion, and here you see it with the apple, okay? If you throw an apple up in the air, okay, at some point it stops going up. Here it goes. Stops going up, and at some point it comes back down, right? And so this is an issue of time, and it's an issue of gravity. They say, look, at some point gravity ceases to act at a certain distance, I guess, and everything should come back down to Earth. And so if we extrapolate this notion to the universe, the matter in the universe, you would think that there's this explosion of matter. And when things get too far apart, there's not enough, the gravity would pull it back together, in other words. In other words, there's not enough momentum to keep them going forever. So at some point, gravity intervenes and pulls it back together into the original ball, I guess, the Big Bang dot, okay, called the Big Crunch when it comes backwards, okay. So that was the notion. And so they said, well, what are we going to prove? We're going to prove that the universe comes back and forms the Big Crunch? And the answer was no. They concluded this, okay? They concluded that the universe expands and expands and expands forever. In fact, they showed that the universe is accelerating in its expansion, not only expanding, but accelerating. That means that things are getting farther apart, but increasingly farther and farther and farther apart. So that's the notion mathematical physics has. Okay, so you have to understand what they're saying. First, you have to understand what they're proposing. This is what they're saying. Okay, so whether you like it or not, just understand it so that you can explain it to your 10-year-old. Okay, so you can say, look, this is what the mathematicians are saying. They're saying, look, there's been a big bang, started 14 billion years ago, created all this matter in the universe, including us at some point. Okay, space is expanding. It's pushing all this matter apart. Okay, and at some point, we thought that everything was going to come back together, pulled by gravity. But what's the issue? Space is what's expanding. Space is a physical object. Space is what's pushing matter apart. Okay? Even though space is matter also, but that's a separate issue. So space is what's pushing everything apart. Okay? That's important to keep that in mind. Why? Because they say there's not enough gravity to pull everything together to overcome the spatial expansion. Okay? So space is stronger than gravity. Okay? There's something in space that we can't see, we can't touch. I don't know why they don't ask those questions to the mathematician when they talk about see, touch in the case of the rope, right? But something we can't see or touch within space, in the properties of space, in the matter of space, in the particles that form space, in the Higgs or whatever, something in there that pushes matter outwards, and gravity cannot overcome that force, that push force. So if gravity is a pull force, this push force, which is within space, is stronger, just pushes everything outwards. There's no way to overcome it, okay? And they say, well, what do we call that stuff? Well, we'll call it dark energy. And dark energy is another word for anti-gravity, okay? Because if gravity is what would pull the universe back together, anti-gravity would be the opposite, right? It's the the outward push, okay? And they say that's called dark energy. Dark because, as always, we can't see it, we can't touch it, we can't smell it. It's very heavy or very powerful, right? But nobody asks those questions in the context of mathematical physics. They allow them to get away with all that stuff, even though these people acknowledge and tell you in your face that they don't know what dark energy is, okay? So they have this energy pushing all the galaxies outwards, okay? And they call it anti-gravity because gravity would pull everything inwards. So if it's going outwards, it's something opposing gravity, and they call it anti-gravity. Another name for it is dark energy. So now you know what dark energy is. It's that stuff that nobody knows what it is, nobody can see, nobody can touch, that pushes all the galaxies apart, which is an ingredient of space, and pushes all galaxies, all stars, all matter apart, right? And gravity cannot counteract that anti-gravity in the long term. In the long term, the universe just spreads out until it thins out until I don't know, until there's nothing left. I don't know. Until everything is too far away from each other. You know, that's the world they have. Okay, and here you have another vision of that, also from Brian Greene's documentary, okay, Fabric of the Cosmos. Okay, and it says, pushing galaxies apart and stretching the very fabric of the cosmos. Okay, and here you have, there's something that fills space and counteracts the pull of attractive gravity. Okay, and that's something they're going to call dark energy. Okay. And again, the expansion is accelerating, as shown in the previous little GIF there. Okay, it's expanding, it's getting faster and faster and faster, and that's how did they determine that? Well, they look at they measure the galaxies and stars in the vicinity, okay, or whatever they can measure out there, and they say, look, we see that all this stuff is getting farther and farther away, okay. And the reason for that comes from the redshift, the notion of the redshift. Redshift is like a Doppler effect. The Doppler effect is that where you have, when you have the train coming towards you, you hear this big sound. and then when it passes, it goes, and what's happening with sound is you're compressing the waves as they come towards you, and when they go away, they get elongated. Okay, so when something is getting farther away from you, you get this lower sound, okay, or this lower pitch, right? And same thing with light, they say. You know, when light approaches you, right, you have the compressed waves, and you have this blue shifted type coloring, okay? When the light goes away from you, well, the wave gets expanded, and now you have this red shift, okay? And so that red shift is identified with something receding from you. That's what they're saying is happening. When they look at the night sky, they say, look, all these stars and galaxies, they're primarily red shifted, okay? The first thing they don't tell you is that we have blue shifted as well. And so you got to explain that. How come we have blue shifted stars and galaxies? That's one issue. The other issue is whether the red shift represents what they think it represents. Okay, and of course I've got a video talking about that, and also in the book, my book, I discuss the redshift in quite a bit of detail, and I think anyone who's read that part has to come to grips with reality, okay? Now, it's got nothing to do with receding stars or galaxies, and there were other people. Halton Arp was one of those, guy who was kicked out of the United States, essentially. They took away his telescope from him because he kept saying that redshift was not synonymous with receding stars, okay? And you got to do your little research. It's a long story to cover today, but redshift does not represent always, under every circumstance, does not represent recession, receding, okay? Receding stars. Okay, so they call this dark energy, this receding of space. They say it's, you might think of it like this, okay? Think of it as something, a gaseous something within space. Here I made it visible, okay? And it pushes everything apart, okay? That's the notion they want to give you of what dark energy might look like if we could see it, okay? They're saying it's something that's in there and it's pushing everything apart, okay? That's the notion. So I don't know if that helps you visualize what they're saying, okay? And of course, they'll never illustrate it because they say it's invisible. And I don't care if it's invisible, make it visible so that I know what you're talking about, okay? So I had to do it for them. There it is. Okay, what's the problem with dark energy? Part of the problem is that most of it is unknown. About 70, I think it's 73, 75% of it is unknown. Here's dark energy. 73% is unknown. They don't know. Here it's light, but it should be dark. Then you have dark matter, another 23% that they can't see or touch. It's got a lot of weight, a lot of mass, okay? And just the luminous matter is very small, only 0.4%. So most of our universe is unseen, very heavy, okay? Either dark energy or dark matter. One is supposed to represent anti-gravity, which is that dark energy there. So I don't know. You got to figure out what these guys are talking about, because they say that 73% is a measure of our ignorance. They say we don't know what it is. And just in case, that 23% is also a measure of our ignorance, because we don't know what that dark matter is. So we have, so far, 96% of ignorance among mathematicians. They don't know what all that stuff is. They just call it dark matter and dark energy because they have no other way of explaining how gravity works. That's what it comes down to. Because of that, they had to turn space into a physical object, and they play around with equations, with formulas there, and variables here, variables there. All they do is put numbers into those variables, values, right, to make their equations come out right. In other words, by that I mean that their equations match what the astronomers observed. So if the astronomer comes back and says, look, we observed this phenomena out there, the guy goes out there and does his measurements, brings the measurements, the so-called theoretical physicist, he puts the equation, he puts values in there and says, well, we can explain it with this model here. This is the model for describing really not explaining, but describing what you see up there. And what they do is put mass wherever they need it. Okay, they fill in the holes with mass. That's the only thing they can think of, and they say, look, if we put mass here and mass there, we can describe what you're observing, and that's how they come to all these notions, these physical notions, these physical interpretations of what's out there, of how the universe works. Food for thought. Okay. Anyways, with that, I guess I'll see you on Wednesday if the corona doesn't get to you. So we'll see you then.